Now we're going to talk about the Coriolis Force, and the Coriolis Force is due to the fact that the Earth rotates on its axis. So if we didn't have the Earth rotating, we would really have boring weather and really would be very mundane and quite predictable, which may be a good thing in some sense. But the Coriolis Force plays an important role, especially on wind direction. So it's really just not a force, it's more of an effect. And again, it's because the Earth is rotating on its axis, which just means that any freely moving objects that are just traveling in the Earth's atmosphere will be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And the Coriolis effect is strongest at the poles and it is weakest at the equator, and actually is non-existent at the equator. And because of this, you will never see any type of hurricanes or tropical systems form along the equator. And you will never see a hurricane cross from the northern hemisphere to the southern hemisphere, because obviously we know that hurricanes rotate, and that means that if there's no effect of the Earth's rotation felt at the equator, there can't be any type of weather systems that happen at the equator. So when we look at a map and we break it down in latitude, here, right, if we were a freely moving object and we were trying to fly straight at the equator, we could fly straight and feel no effect of the Earth rotating. Now you go up to the mid-latitudes, so basically about 40 degrees north latitude. Here's a picture of the United States. If we were somewhere out in California and we were to fly straight all the way across to DC, well, we couldn't really fit a straight line to that like we would driving in a car. Because the Earth is rotating beneath us, we would actually be deflected, and instead of ending up in Washington, D.C., we would probably end up somewhere, maybe Atlanta or something along the lines of that. Now you go higher up in latitude, you can see here, based on the arrows, the deflection is also quite large. So to break down the effect of wind in our atmosphere, especially at upper levels, we look at this diagram. And so here we have high pressure in the warmer climates. So anywhere near the equator would be relatively areas of higher pressure because it's warmer. And here we have low pressure up towards the poles because of the temperatures being cooler temperatures. Therefore, we have lower pressure. So when we look at this map, if the Coriolis effect wasn't a thing here on Earth, we would have all of our wind be basically from the south. So here would be how the atmosphere would stabilize. It would go from the south and it would travel north. It would go from high pressure to low pressure. But because the Coriolis effect in the northern hemisphere will direct things to the right, here we have wind that will want to travel from high pressure to low pressure, or in this diagram we have blowing from the south to the north, but the Coriolis effect will turn it to the right in the northern hemisphere. And so that is the resultant wind, which is called geostrophic wind. And geostrophic wind is wind that will flow parallel to isobars. And on a 500 millibar map, this becomes very important, and it also becomes very noticeable. So here in this picture, this is just an image of 500 millibars, which is about 15,000 feet up in our atmosphere. Now here on the left-hand side, you notice these numbers. We have 5790, 5730, and at the very top we have 5190. So these numbers are the height of 500 millibars in meters, because remember, 500 millibars, depending on where you are, varies. It's not just a fixed altitude. So in Massachusetts, 500 millibars in the month of April might be, let's say, 10,000 feet. But in July, 5,000 millibars might be 15,000 feet. Why? Because July or the summer months would be warmer and the spring months would be cooler. So therefore 500 millibars would be lower in the atmosphere because the atmosphere is more compressed. So we can plot 500 millibar heights on a weather map and we notice these ridges and these troughs. So in a ridge, places that are under the ridge experience higher pressure and relatively warmer temperatures. And people in a trough are susceptible to cooler temperatures and areas of low pressure. And you can also notice this geostrophic flow here. Geostrophic flow is wind that flows parallel to isobars. And so that's what geostrophic flow is. It's wind that flows parallel to isobars because it is a balance between the pressure gradient force and the Coriolis force. So the resultant wind would be in the United States traveling west to the east, and this is what's known as the westerlies. And this is the predominant wind direction in the United States. So when we look at a real-world example of a 500 millibar map with troughs and ridges, here you noticed that here would be a ridge out towards the west coast. In the center part of the country, here would be a trough. And then we also have another ridge out towards the east coast. So this was in October of 2016. So this is the 17th of October of 2016 at 12 Zulu. So this was the 8 a.m. run because it was still daylight savings time here. But you can see, based on the colors which indicate temperature and the temperature keys at the bottom, this would be warm temperatures, or locations that are under the ridge are experiencing warmer than normal or above normal temperatures. People in the middle part of the country in the Central Plains, they're experiencing colder temperatures. You can see by the darker blues. Here is your trough. And then out in the East Coast, we have another ridge. Again, you can see the warmer colors. And so here, when we have a ridge, that means warm air is able to come up further north. And then when we have a trough, that means cooler air is able to pull in towards the south. So looking at a 500 millibar map, and we're going to talk way more about this later on, but this is very important, and this becomes a very important key aspect to when you're forecasting, because when you look at a 500 millibar map, you know that a area that is underneath a ridge is going to be warmer than normal, and they know that they're going to be experiencing more high pressure or sunny days. Troughs are going to experience cooler weather, and they're going to be more susceptible to wetter days, more precipitation. So when you look at this map, you already know who is experiencing what in the entire country, and you are able to really just do a nice general scan of these weather features. So when you go down and you look at surface features, you have a much better idea of what you're looking for.